Again, if you have question or answer, just interrupt me, okay? Don't worry, don't be shy. Just let me know if you see the presentation now.
Yes, Professor.
Okay,
Let's see.
thank you very much. So basically, what about the transmission network? The transmission network is the part of the power system that is in charge of transferring the power from the produce power plants, okay, and the customer areas, okay. Here I'm saying customer areas and not final customers, because as you know, the transmission network cannot go too near to the final users, okay? So basically it has to transfer power from, I would say here, big power plants to the customer areas. So basically here I would say to primary substations, okay? And in terms of copper and iron, the main part of the transmission network are basically two, okay? So lines and transformation plants. So basically the two main elements of the transmission network are lines and transformers or transformation plants. Based on the voltage level, you can distinguish between extra high voltage and high voltage. So those numbers here are for the Italian case. Probably you in Vietnam could have different numbers, but basically you normally the transmission networks do not have a single voltage level, okay, but they have at least 2 or even 3 voltage level, okay, so more than 1 voltage level. And they are used for long distance, okay? So basically, I would say greater than 100 kilometer, okay? But even less. Then it depends on the geography of the area. The transmission network is completely controlled and managed automatically. What does it mean? When you are hearing in these days smart grids, okay, basically smart grids refers to distribution network, okay. You probably know already this, but why smart grids normally refers to distribution network? Because the transmission network is already historically smarter, okay? So the transmission network is already smarter than distribution network, and I will let you know more later on, okay? And another characteristic of the transmission network is that it is meshed. What does it mean, meshed? Meshed refers to the topology, okay, of the transmission network, and having a meshed power system, this in general guarantee a high level of security, okay? So the more, it is not completely true, but the more the network is meshed, the more the network is reliable and resilient, okay? Meshed means that if you have a line trip, okay, all the substations, so all the customers remain fed. So you don't see an interruption when you have a fault. if you think about your household, okay, if you have a problem with one of your devices, okay, maybe you have a short circuit or an overcurrent, okay, the switches that you probably have installed at the entering when the power system enters your household trips, okay, so it interrupts the connection in, in order to extinguish the fault or the overcurrent, okay. Basically, when you have the trip of your protection device, you completely lose the supplying of energy, of electricity to all your household, all your house, okay. For the case of transmission network, that's not the case. Even if you have a fault, you have a trip of one of the protections, you don't lose the electricity to the substations, okay. That's good because you guarantee to still have electricity that goes to the final users, even if you have one faulty line, okay. Normally, this is called n-1 security, okay. N-1 means I have n elements in my power system. I lose one, I still have electricity to all my final customers. So the system is n-1 security. Even the protection, the protective system is very sophisticated and redundant, okay? So we have very special protective system, and the protective systems are redundant, etc. So basically, the transmission network, as they are now, they are already smart, okay? So you have to keep in mind this. What about generators? Which are the generators connected to the transmission network? So basically, the generators connected to the transmission network, at least in Italy, are the one greater than 10 megavolt ampere. I just want to ask you a question. Given this number, 10 megavolt ampere, which are the renewable energy sources which are probably connected to the transmission network? Would be, I would say, wind or PV. So what's your idea? You would expect to have more wind or more PV power plants connected to the transmission network, since the minimum power you should have to connect them is 10 megavolt ampere. Wind or PV? Normally, between wind and PV, which is the power plants with the higher power install, normally speaking, not taking the exceptions, but normally wind or PV? Normally are wind power plants, okay? So the wind power plants, almost all of them, at least in Italy, are connected to the transmission network, okay? We have also some PV power plants connected to the transmission network, but are not so it is not so frequently, let's say. Okay, so this is a very interesting website. I would like to show you. Can you see my browser now?
Yeah, we can see.
Okay. Basically, this is the website of ENTSO-E, okay? This is the association of all the European transmission system operators. Okay, and from here it is very. So I'm sorry that Vietnam is not here, but basically from here you can see the transmission network of the whole Europe, and even not just Europe, also Turkey, Azerbaijan, Ukraine, Russia, and so forth. So basically here the TSOs just to share the topology, okay, of the distribution network. So look, this is quite impressive, okay. Basically nowadays, at least in Europe, in all the areas you can find electricity. Okay, so that's the reason why, and it is mandatory for the TSOs to, and then to DSOs to give electricity to the final users. So basically you have many transmission networks. Okay. So here you have the legend. So basically the red lines are at 380, 400 kV, okay? While the green one are at the lower level, like 220 kV, okay? Moreover, you have some pink lines, okay? For instance, here. What's the meaning of these pink lines? Do you have an idea? While yeah, please.
DC network. Yeah.
Yeah. So basically, those lines here are DC networks. Okay. I will let you know later why for these connections in particular. So look, almost all of these connections are under the sea. Okay. For instance, this connection here connect the continental Italy to Sardinia, which is an island close to Italy, which belongs to Italy, but you know you have many kilometers between Italy and this island here. So basically, for some connections, especially in the Northern Europe, the DC is more convenient than AC. I will show you later why. So basically, has I don't know if you remember the video I showed you at the beginning of my lectures. Nowadays, DC and AC are working together. Okay, so basically the DC come back to be feasible and an interesting option in some specific situation that I will detail you later on. Moreover, if we just keep the cross-border connections only, okay, the map just show which are the lines that are crossing the border between two different countries. And from here, you see that basically Italy is well connected, okay, because it's connected to Switzerland, it's connected to Austria, Slovenia, Croatia here, France here, and here in the future with Montenegro, okay, and here to Greece. So basically, what we are doing now is to have a power system which is not the Italian power system, the French power system, but the European power system. These have some advantages, and one of the advantages is that the power system is more stable. So the bigger is the power system, the more stable it is. That's more or less the idea. I will come back to specifically for the Italian power system, okay, but from here, okay, so this is the northern Italy and this is the south. Look, in the northern part, you have much more transmission lines than in the center and in the south. Okay. Why? Because basically, as I told you many times, the load is concentrated in the north. So we need more transmission lines to supply the energy, the power required from those loads, while the center and south has just few lines, cause the load it's not very very dense. But as you already know from my previous lecture, if we install transmission, if we install big power plants from RES in the south, look, from the south to the north, we just have this line here, this line here, this line here. So we just have few lines, a few lines, which basically does not give many opportunities of bringing energy from here to here. Okay, I just want you to notice this area here, where apparently we do not have any transmission line. I will come back to this later on. Okay, but basically, look here, you don't have many lines, and I would like to show you later which is the reason why. Okay. Anyway, you have this link, so maybe you can just try to explore the European network. Okay, so why DC sometimes is more convenient than AC? Okay, so first of all, when DC, okay, becomes economically preferable than AC, basically when you have a line, okay, so here is a primary substation 1, primary substation 2. When this line is between 300 and 800 kilometer for overhead lines, or between 50 and 100 kilometer for underground cables. Okay, so if this length here is in this range, the DC is better than AC. Okay, but which is the difference between DC and AC? Why DC is more convenient than AC in some cases and not in others? So basically, let's look to this flow chart here. If you just have an AC power system, basically you have a generator here, right? Then you have a transformer, okay? Let's say from medium voltage to high voltage. Then you have an HVAC line, okay? And then you have another transformer, or more than one, I would say, and then goes to the final users, okay? Here it's basically more than one, but just to make these things easy, okay? So for an AC connection, you have, as I told you already, lines and transformers. But if you want to move from AC to DC, you should also have to have a conversion, okay? Before from AC to DC, and then from AC to DC again, okay? No, sorry, from AC to DC, and then from DC to AC. Okay. So you generate electricity in AC. Then you convert from alternating current to direct current. You use an HVDC, so a connection in direct current, and then you convert back from DC to AC because the final users normally have devices in AC, okay? So the final users works in AC, okay? So basically you have to go from AC to DC, but then back to DC to AC, okay? Basically, so the traditional power plants are still in AC, okay? But if you consider, for instance, a photovoltaic power plants, it will be in DC, okay? So if you assume to have the generation in DC, and let's assume to have for a second the final users in DC, okay? So you would have lights, refrigerators, oven, all in DC. Basically, having you would not have the converter, okay, because you are producing in DC and consuming DC. So you would skip the two converters, and so basically the DC would be very, very convenient, okay, because you are generating in DC and consuming in DC. In that case, the DC would win for sure, okay? Nowadays, that's not always the case, because let's consider to produce in DC, but you are consuming in AC. So basically you cannot skip those two converters here, okay, which are quite expensive, okay? So to clarify this, just have a look to this chart, okay? Here you see the increasing of the cost, so the investment cost on the y-axis, while on the x-axis you have the project distance, okay? So the more is the distance between the generation and the final users, the more is the cost of the transmission system, okay? But where is the difference, the main difference between AC and DC? The AC terminal cost, so basically this substation here and this substation here are quite less costly than the cost of having the transformer and the converter together, okay? Here, let's say just TR. Here is TR plus converter, okay? Converters, TRs, okay? So basically, there is a gap in the investment cost related to the converter stations. But at a certain point, if the length of the connection becomes higher and higher, there is a break-even distance from where the DC becomes more convenient than AC, okay? Why? The reason is here, okay? The stations DC are greater than AC, okay? But basically, what about the lines? The DC are more convenient than AC. Why? Because consider that normally for an AC, you have 3 wires, right? For DC, you have 2 wires or sometimes even 1. Okay, so here you have 3 wires, and here you have 2 or 1 wires. For subsea connection, normally you use 1 wire and you do the returning path through the ground, okay? You just need 1 instead of 3. you can imagine that if the length increases, the cost of the cables weight more AC than DC, okay? So the conclusion of this is that for very long connections, it's better to have DC. For shortened one, AC. But moreover, I would also add this: if the final users would be in DC and the generators again in DC, probably due to the cost of converters nowadays is not high as in the past, the DC connection would be preferable than AC. Okay, but you can imagine that having especially this, all the final users in DC is not a very easy task. What about the Italian transmission network? Here, I just want to highlight this concept. Look, this is the orography of Italy. Okay, I don't know if you know more or less how it is done, but basically all this part here are very high mountains called Alps. Okay, so here you can get to high, like I'm not very expert, but I would say between 3,000 and 4,000 meter. Okay, and then you have also these mountains here, okay, which are called Apennini. Okay, so if you look to the left picture, which is the Italian transmission network, here you can notice that this part here does not have many transmission line. Why? Because the orography does not allow, or it is much more expensive to have transmission lines here. Okay. And what about Alps? Okay, look, in this part here, you have some lines, but basically since in this part of Italy you have many rivers, lakes, so water, you have many hydropower plants. Okay. So basically the lines you see here are just to bring the power from the hydro to the final users. But basically, even here, the very high transmission lines are mainly, are mainly here, okay? So where are the transmission lines mainly in Italy? Here, 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 basically. So which corresponds to the area where we do not have mountains, basically, okay? So maybe you have a similar situation also in Vietnam, but that's more or less the case, okay? When you are investing in transmission lines, you also have to consider this. Back to the things that I stress many times. Let's consider to have let's consider to have the generation from wind and PV here. Okay, wind and PV here. So basically, look, if you exclude this red area here, you do not have many paths. Okay, so you should have to bring all the power to the north. Okay, just using those two corridors here. So basically, you have a sort of bottleneck. Okay, so having a huge amount of RES in the south would be good because you can produce economically energy from renewable sources, but basically then you have the problem of bringing this power from the south to the north. Okay. So here I just reported a picture of the northern area and a picture of the southern area, just to show you the difference between the north, a more dense, many transmission lines, south just few transmission lines. Okay, because the load is less. Here, just to let you know, so those two charts here are from the same website of Turner I showed you last time. Basically, what you could see here is that the internal physical power flows changes within the day hours. Okay, for instance, you see that at 10 a.m., so 10 in the morning, when all the activities start running up in the morning, the power flows goes from the south to the north. Okay, vice versa, in the evening, okay, the power goes from the north to the center, let's say. Okay, so if you have a look to the exchanging in power between north, south, and center, you will have a very different situation hour by hour. Here is the transmission network in a schematic form. So how the transmission network is made. So basically, here you have a very high transmission network, okay? Then here you have a transformer that drops the voltage to a lower level, which is this one, okay? Again, here you have a very high transmission network that brings the voltage down to a lower voltage. And then you have many primary substations, okay? Which in this chart here are all these red and, sorry, the red arrows are these transformer plants here, while the green ones, okay, are this primary substation here. So basically, you have to imagine here to have at least two lines coming with two transformers, and then from here you have the medium voltage feeders, which are not showing in this picture here, okay? But basically, in each of these points, okay, look, you normally have one line coming, one line leaving, at least one coming and one leaving, okay? In this case, you have three lines. That's for the same concept of reliability. So basically, the power can flow this way, this way, this way, and then maybe also this way, okay? Okay. So when I say that the topology of the transmission network is meshed, what does it mean? It means that if you consider a single primary substation, for instance, this one, the power can go from two different sources, two different paths, okay? The first path is this one, right? So the power can goes from here, P1, or the power can goes from here, okay, P2, okay? So in normal operation, the power that goes here, P1 plus P2, comes from two different paths, okay? The left one and the right one. Let's assume to have a fault over here. Okay, so let's assume to have a fault on this line here, okay? what happens? It happens that P1 becomes 0, okay? Because the power cannot go from this direction. But what about P2? P2, so let's say here is P1 first equal to 0. What about P2? P2 first is equal now to P2 plus P1. Okay, so basically the power automatically rerouted on the safe path. Okay, so in this case, you are able still to give P1 plus P2 at the distribution network, at the final users, which will not see anything, any change. Okay, just the power will not flow from left and right together, but just from the left. Okay, that's very nice for the reliability of the system. Starting from the primary substation, we have what is called the distribution network. Okay, so basically this is the border between transmission network and distribution network. Okay, so here you have the transmission network, and basically here you have the distribution network. Okay, I hope this is almost clear. What about the distribution network? So let's move to the last part of the power system. So the distribution network is basically the last phase of the electricity process. And as I told you also last lecture, what we are doing, using some transformers, we are reducing the voltage level, okay? So with one transformer, we goes from high voltage to medium voltage, and then from another one, from a second transformer, we go from medium voltage to low voltage, okay? So here you have the voltage levels which are common in Italy, 1520 kV, 400 volt 3-phase, 230 volt 1-phase. Okay. The medium voltage distribution networks are fed by primary substation. Okay. So the primary substation, which are, for instance, this one, are feeding the distribution network. Okay. And then from the primary substation, you have some feeders. For instance, this is one feeder. This is another feeder that are supplying some secondary substation. Okay. So the power goes from here to here, and then from here to here, etc. So basically, the feeders are the part of the power system that take electrical energy from primary substation to secondary substation. Okay, and the secondary substation is the part of the power system that convert from medium voltage to low voltage. Okay, so basically you have primary substation from high voltage to medium voltage. Then you have what is called medium voltage feeder. Then you have what is called secondary substation, when you have another transformer from medium voltage to low voltage. And then you have what is called low voltage feeder, which goes to the final user. Okay, and here you have the transmission network, another transformer, and then you have a generator, for instance. Okay, so this is the whole path from the generators to the final users. Okay, the medium voltage networks are generally structured in a mesh fashion. Okay, so both transmission and distribution networks are meshed, but that's the important. things are operated in a radial configuration. Okay, what does it mean, radial? Radial means that the power can flow just in one direction. Okay, let's back to this scheme here. Okay, let's consider a final users here or a final users here. Those users can receive power just from this path, right? This is the path of the power. Why not as here on the right side? Because look, here you have an open switch. Okay. So basically the power just goes from left, not from right. Okay. So this way of operating the distribution network is called radial operation. Okay. So this is a primary substation in a schematic form. Okay. So what you have mainly in a primary substation, okay? So the primary substation goes from high voltage to medium voltage. In a primary substation, normally the core the core is the transformer from high voltage to medium voltage, okay? Which normally has this kind of device, which is called a regulator, that helps in controlling, okay, the power system voltage level. Okay, so with the regulator you can change the ratio of the ratio of the transformer, so that you can adapt the voltage you have here, VHV, with the voltage you have here, VMV. Okay, so changing the ratio, you can change the ratio between the VHV and the VMV. Okay, so basically if you have a high voltage here, you can use the regulator to keep this value constant, so to reduce the voltage level here and vice versa. Okay, look, the primary, so all the elements, all the devices in the primary substations are in couple. Okay, look, in a single primary substation you have one transformer here and another here. This is for reliability. Why for reliability? Because let's consider to have a fault on this transformer here, all this part will remain unsupplied, okay? Because this part here is supplied by this transformer here. But basically, if you close this switch here, you can bring power again, passing to the left side transformer to this part of the distribution network, okay? Vice versa, look, if you consider to lose this transmission network, what does it mean? You can, what you could do, you could close this switch here and bring power again to this transformer here, okay? So normally the two transformers are operated with this switch open, but in case of problems, you can close them and have a backfeeding option, okay? So this system is very reliable, okay? Very, very reliable. You cannot, you don't have to lose the supply of the feeders, the medium voltage feeders. So basically, you adopt this approach of having double devices. So the same device so you double all the devices, okay? Transformers, HV bus bars, medium voltage bus bars, etc. That for reliability reasons, okay? So this is basically the topology of a medium voltage network in detail, okay? So primary substation 1, primary substation 2, okay? From here, what happens? You have medium voltage feeder 1 and medium voltage feeder 2, okay? Medium voltage feeder 1, medium voltage feeder 2, okay? Then here you have some secondary substations in which you have a transformer from medium voltage to low voltage, and from here you have the low voltage network, okay? If you look to this topology, you can recognize that is meshed, right? So the topology is meshed. Why is meshed? Let's consider this secondary substation. Look, the secondary substation is connected, okay, to, this is the first path to one primary substation, and this is the second path to a secondary primary substation, okay? So basically the topology is meshed. But what about the operation? The operation is radial. What does it mean, radial? Look, the radiality of this system is given by this switch here. Because this switch disconnects, okay, medium voltage feeder 1 from medium voltage feeder 2, okay? So the power cannot flow here, okay, because the line is interrupted, okay? So basically, the topology is meshed, but the operation is radial. So this SS1 and this SS2 receive power just from PS2, okay? And this one, and this one receive power just from PS1, okay? So the power flows is just in one direction in the feeder. This direction here and this direction here, okay? So the question would be now, but why having a meshed network? Having a meshed network is for reliability reasons. Why for reliability reason? Let's consider again to have a fault over here. So you lose completely this path, okay? Here the power goes to 0. This, and this remain unsupplied, right? So the power cannot flow anymore from PS1. But you have an option. You can close this switch and supply the 3 secondary substation from PS2. Okay? So now the power goes again to here, but can also go this direction. Okay? So basically, using this switch here, you can supply these 3 secondary substation with PS2. Okay? So just to recap, in normal operation, you keep the distribution networks working radially. Okay? So this switch is open. Okay? But in contingency, if you have a fault, you can close this switch here. Okay? And supply those secondary substation with PS2. Okay? Of course, when you have the fault here, these customers feel an interruption. These does not happen in transmission network, which are operated meshed. Here, since you are operating radially, the secondary substation, you lose for a while the supplying, but then you fast backfeed them from another feeder. So you have a quite reliable system again. Okay. What about the last part of the distribution network, the low voltage network? Basically, the low voltage network starts from a secondary substation, okay, medium voltage to low voltage, from which you have some low voltage feeders, okay, low voltage feeder 1, low voltage feeder 2, okay. And basically here, look, the power, okay, goes to the final users, which are those points here. What happens if you have a fault over here? If you have a fault over here, this switch will interrupt the power flows, okay, here, and you will completely lose these customers. Why you are completely losing? Because look, you do not have a possibility of resupply customers from another safety feeders, okay? You don't have this connection here. So basically, in this case, you lose completely the supplying of energy to the final users till you recover the faulty branch. But this is acceptable. Why this is acceptable? Because the number of customers you are losing here is much less than the number of customers you can lose if you lose 3 secondary substations at the same time. Okay, so it is a trade-off between the cost of making the network meshed and the cost of losing the supply of energy for the customers. Okay, so this is more or less how the power system is made. Okay, just to clarify some points, let me show you a software. I don't know if you hear about if you hear about this software, which is called PowerWord. Okay, so this is a software I normally use in my lectures. Okay, because it's quite nice to understand how the power system works. Okay, and if you go to this link here, you can download the software for free. I think you have a limitation that just up to 40 passes. Okay, so you can download the software and you can play a little bit with power system. Here, at least at this link instead, you have some courses which you can follow to understand how it works. Okay. Let me show how it appears. You see the software now?
Yes.
Okay. So basically, the software is let's say, traditional power system software for analysis. Okay. And basically, the idea is to having 2 different modes, the edit mode and the run mode. Okay. The edit mode allows you to build the scheme, the topology of your power system. For instance, if I double click on this generator here, you have some information now about the generators. For instance, the power, the medium voltage set point, active power, reactive power, the set point of the voltage, and stuff like that. If I double click on the transmission line, I could say the line is open, closed, which is the length. So you are electrical engineering, so you could be able to understand very easily what I'm saying. For the transmission lines, you can give to the software the parameters, so resistance, reactance, etc., the thermal power limit. And for instance, for the load, you just give the active power, the reactive power. So you have to give to the software more or less all the information you need for running a power flow, okay? And for the transformer, you have the resistance, reactance, the tap ratio, etc. So once you have it, okay, if you go to the Model Explorer, okay, basically the Model Explorer just gives you the inputs data and other very interesting things such as the YBAS, okay? You should know the meaning of the YBAS. So the YBAS is the metrics used for running power flows, okay? So the software automatically builds up the Y matrix, and once it has it, it's ready to run power flows, okay? So I went very quickly, but I don't want to let you know how to use the software. You can learn it by yourself. It's not very difficult. But if we go now to the run mode and to tools, okay, the software allows you to make many simulations, and one of the simulation is, of course, the power flow, okay? For the power flow, you can set up many, let's say, many parameters like the tolerance, the number of iteration, etc. And basically, if you run the power flow, okay, okay, so here you can also decide which kind of power flow you want to run. So Newton-Raphson, Gauss, DC, okay? Probably those numbers are familiar to you. And basically, if you click on play, the software show you very clearly, you know, the power flows. The active flow, which is here in red, and the reactive flows, which are in blue, okay? So what you can notice from here is that if you consider this load here, it receives energy from two paths, okay? This one and this one. If you sum up 63 plus 77, you end up with 140 megawatt. And so this is the meaning of meshed topology and meshed operation. Why is a meshed operation? Because look, the load is receiving power from two different paths, these paths here and these paths here. Let's consider now to have a fault on this line here. So, and to open the related switch. Okay, so what happens in the power system? The power system automatically, as I told you, rerouted the power flows, okay? So that now the load is applied just from one single path, okay? And basically, it doesn't felt any interruption, okay? When I open this switch, look, the load always receive the same power with this line or without this line, right? Okay. So basically, this system is quite reliable. So this number here is too high, okay? But but that's not a big issue. We can manage this. But the idea is that if I lose one line, I do not have particular problem. So just consider to lose this line here, okay? No problem. Power goes from two other paths, okay? This system is basically not n-1, but n-2 reliable, because if I lose this line and if I lose this line, the system is still able to supply the final load, okay? So this system is n-2 reliable. But what about if I lose even this third line here? Okay, I will end up with a blackout. Now the load, look, the load is at 0. Okay, but before going to 0, I lost 3 different transmission lines. Okay, so it's a quite reliable power system. Okay. I think it should be clear the meaning of meshed operation. But what about distribution networks? Okay. Distribution networks are quite different, okay? So here I try to summarize the power system from the generation, transmission network, primary substation, okay? Primary substation, feeder 1, medium voltage feeder 1, medium voltage feeder 2, secondary substation, low voltage feeder, final users. Okay, so in this chart, you have a very simplified power system. Okay. Okay, so this is the power flow. Look, even the distribution network is meshed. Okay, because look here, I have an open line. Okay, I keep this line open because I want the power flow goes just in one direction. Okay. Okay, from left to right, from left to right. Clear? So from left to right, from left to right. What happens if I have a fault on one of the distribution line? Let's try. Immediately, this load remain unsupplied. Okay, so this topology is less reliable than the transmission network. Okay, why is less reliable? Because if I have one fault, I completely lose part of the load. Okay. Even here, if I have a fault here, I completely lose this part of the power system. So this system is not n-1 reliable, because I lose one device, one element, I completely lost an area of the power system. Okay. But why I keep the topology radial? Because look, if I have a fault on this line here, okay, I can close this line here and resupply this load with the other feeder. Okay, so I'm backfeeding this load with this feeder here. Okay, once I fixed, okay, once I fixed the fault on this line here, I can reopen here, reclose here, and be back to the original topology. Okay, so even in the distribution network, we have a meshed topology, but the operation is radial. So if I have one fault, I lose one part of the power system. Okay, that was not the case for the transmission networks. I hope these two schemes clarified a little bit the my explanation. So guys, it's clear more or less up to now. Can you give me a feedback?
Yes, Professor, we understand clearly.
Okay. So just one thing before having a short break. Now I just want to show you the distribution network of Milano, okay? The city of Milano. Which will really surprise you. Okay, so Milano basically is, so this is Italy and Milano is in the northern part. Okay, is here, is this area here. Okay. Okay. So can you tell me more or less how many primary substations, in your opinion, are feeding the area of Milano, the city of Milano? How many? 10, 100, 1000 primary substation. So from high to medium. Do you have any idea? How many primary substations are there? Please don't be shy. 10, 100, or 1000?
Maybe around more than 100.
So more than 100 primary substation from high to medium. Okay. Basically just 11. Okay. So the area, the city of Milano is supplied just from one, just by 11 primary substation, which are the squares you are seeing now. Okay. I just want to focus on one of them. Okay. This is one of the biggest primary substation in Milan. Okay. So basically from here, it is very easy to recognize the high voltage part of the primary substation. And here you have the transformer from high voltage to medium voltage. Okay. So basically you have some high voltage cable that goes from this direction to here. Okay. And then the transformers. Okay. So basically from here, you have the medium voltage feeders that goes all around the city. Okay. So the answer was more or less 10 primary substation. Okay. 100 is a much huge number. Okay. The second question is how many secondary substation we have in Milano? 100, 1000, 10,000. Please try to guess. How many? 100, 1000, 10,000.
Maybe 1,000.
Maybe 1,000. Okay. No, we have 6,000 secondary substations. Okay. So in each of this circle here, you have to imagine to have a transformer, okay, from medium voltage to low voltage. Okay. So look how the power system is complicated. Okay. I just want to show you this, because from the slide, maybe you can think that the power systems are quite easy, okay? But from here, you can recognize that are not easy at all, okay? So basically, each of these circle here receives energy. And from here, you have some medium voltage feeders that goes to the final users, okay? And what about the medium voltage feeder? How many kilometers of lines you think we have? 1,000 kilometer, 2,000 kilometer, 4,000 kilometer. You will be probably shocked about what is appearing now. So just in Milan, we have more or less 4,000 kilometer of underground cables. Okay. So what you're seeing here are all the cables, all the medium voltage cables, which are bringing electricity around the city of Milan. Okay. Look, since so if you are walking around Milan, you cannot see anything of those cables, any of them, because are all under the streets and on the sidewalks. Okay. But look, you have like a spider net, no? It's very dense. You have feeders all around the city. Okay. You can imagine that dealing with this power system, it's not very easy. Okay. Not very easy at all. But moreover, overlapping this medium voltage network, you then have the low voltage network, okay, which is more or less at the same shape of the medium voltage one. It takes a little bit of time. Okay, so here it is in the same color. Okay, but basically you have let me try to color this in a different way, if I can. So basically you have something similar to okay, so you have something similar to the medium voltage network, okay, but in this case is lower voltage network. Okay, so look, is a completely mess situation. Okay, this is the Duomo Church, the most famous church in Milan. Okay, so let me try also to switch on the secondary substation and the primary. So substation. So this is more or less how a real distribution network appears. It's very, very complicated and tough to make this network in operation. Okay? But just to be maybe more clear, okay, so this is more or less how so let's back to our power system. So this is a primary substation. Here the primary substation is inside this building, and from here I have this feeder goes out, okay, and then goes to some secondary substation. Okay, so here the feeder enter and exit, and it goes to a secondary substation, in, out, okay, then in, then out, in, out, etc., till the end of the feeder. So this feeder is quite long, basically. Okay. Then finally, here I just focused on one primary substation, a secondary substation. Basically, when you from this secondary substation, you have other feeders but are low voltage feeders. Okay, so power goes up to here. Then from here, I have another transformer from medium voltage to low voltage, and then some lines, some low voltage lines that goes, look, really to the final users. Okay, so here you have the household meter, household meter, household meter, etc. Household meters. Okay. So here is more or less how the power system, a real distribution network appears. Okay. Okay, so I think that we can have like 10 minutes break. So we can come back in 10 minutes and start again speaking about the impact of RES on transmission and distribution. Okay. So see you later.
Yes, Professor.
Okay. May we restart?
Yes, Professor.
Okay. Okay, so let's see now the integration and the pros and cons of connecting REST to the power system. So basically, we have already investigated some of the consequence of the power of the integration of REST in the power system. Now I would like to go in more details. Okay. So what about RES and dispersed generation? There is always there are always some misunderstanding, you know, between RES and dispersed generation. So basically, the main difference. So if we consider generators, okay, the main difference is between large and medium small sites. Okay. Basically, RES. They could be connected both to the high voltage network and to the medium low voltage network. Okay. So if you consider the traditional power generation units, let's say thermal, nuclear, they were almost all connected to the high voltage network. Okay. But in the case of RES, we will see that basically that's not completely the case. Okay. Normally, as I told you already, the large scale RES are normally for wind. Okay. While the medium small scale are normally for PV. Okay. At least in Italy, as I told you, what they are called dispersed generation are the units lower than 10 megavolt ampere, okay, which are normally connected to the medium voltage or low voltage systems. Okay. Within the dispersed generation, you could have RES, but you could also have CHP, okay? Combined heat and power plant, okay? So normally the kind of RES connected to the medium and low voltage networks are CHP, which they could be renewable or not, because if you use as fuel, let's say the biogas, they can consider even CHP as RES, but if you are using gas, for instance, you cannot consider them as renewable energy sources. So we have CHP and RES. Okay. Here you have the scheme of, basically this is a primary substation, okay? And here you have a scheme of a distribution network in which you see that you have some generators installed, okay? On the medium voltage side, but also on the low voltage side. Okay, so nowadays we are seeing the installation of many dispersed generators on medium voltage and low voltage networks. Okay, the installing of these DGs could impact both transmission network and distribution networks. Okay, and they are impacting transmission networks and distribution networks in a different way. Okay, so some issues arise in transmission network due to DGs and some others on distribution networks. Okay, I titled this slide the energy revolution scenario. What does it mean? Basically, as I told you also last time, we always have to consider the thermal power plant, okay, and the rest together, okay. Why? Because the rest impact the thermal power plants and vice versa, okay. Here, okay, you see the map of Italy with the power from thermal plants from 2002 to 2011. Okay, so basically from 2002 to 2011, we had an increase in the thermal power plants by 21,000 megawatt. Okay, more or less shared between north and south. While from 2011, when PV and wind start increasing, the power installed of thermal power plants, it is just few megawatt. Okay, look, we have something here and something here, just. Okay, so the consequence of having installed RES is that many the investments on thermal power plants suddenly dropped in 2011. Okay, so the money were shift from traditional power plants to RES. Okay, that's good because it means that the investors prefer to go with renewable energy sources. But what's the consequence of that? The consequence is that basically, even before 2011, here you go from 2006 to 2011, the annual utilization hours of thermal power plants by natural gas drops by minus 40%. So what does it mean? It means that if you had in 2006 a thermal power plant that of 1 megawatt, okay, you will produce 5,100 megawatt hour. Okay, let's consider to have like to get from the selling of this energy 1,000 euro megawatt hour. Basically, you get like giga no, sorry, mega 1, 2, sorry, euro, okay? If I didn't make some mistake in computation, if I have a thermal power plant of 1 megawatt with this number of utilization hours and with the price of energy of 1,000 euro megawatt hour, in 2006, I would get 510 kilo euro. What about in 2011? In 2011, I would just get 310 kilo euro. Okay. Do you think I'm happy for that? If I am the owner of a thermal power plants, I'm not happy. Okay, because I reduce my income by 40%. Okay. That's also the reason why from 2011 there were just few installation of thermal power plants, because most probably the installation of thermal power plant is not convenient anymore, because I don't get enough money. I cannot work for enough hours to recover my investment. Okay, so the installation of RES brings to this very, let's say, not very easy situation for the thermal power plants, which is one of the goal, basically. I don't want to say that it's bad, but basically this change completely the scenario generation. Okay, look, I already showed you, but look, from 2010 to 2011, due to very strong incentives for photovoltaics, we were a huge jump of the PV. Okay, you can imagine then in 2011 we overcome, so let's consider 2012, we overcome by plus 85% the target the government imposed for 2020. Okay, so the government said, okay, in 2020 we would have 8.6 gigawatt of PV, but due to the incentives that they introduced, there was a very high jump, and in 2012 we already get almost double than the what was expected in 2020. Okay, but where wind and PV are installed in Italy? Look, as I showed you already, most of the power is in the southern regions, so Puglia, which is here, Sicilia, which is here, Campania, which is here, for wind and PV. And then we have some PV in Lombardy and something in Sardinia. Okay, but most of the production from RES is from the south. Okay. So here you have the requested connection for wind and PV. So when you want to build a new power plant, you have to make a request. And here you can see the number of requests for wind and for PV. What we can notice from here. Basically, look, most of the wind were requested in the south. Okay. Basically, just because here it's more windy, While for PV, For PV is the same. Okay, most of the request connection to the transmission network. So, okay, here I'm referring to the request of transmission network. So plants with a power greater than 10 megavolt ampere. Even for the PV are in the south. Okay. Here probably the reason is because of the space available. Okay. And so it's more, you have more radiation, but even more space for building big power plants. Okay, so look, in the northern part, you just have few requests of connection for wind and PV. Okay, so basically here you have the same issue as always to bring this energy from the south to the north. Okay. So let's have a look now at the RES impact on the transmission network. Basically, the transmission network, okay, do not require, okay, substantial changing in order to face the RES. So from this first sentence, it seems that the transmission networks are already ready, okay, are ready to host renewable energy sources. That's a good news, no? Okay, because basically we have already a power system that was not specifically designed for RES, but it's ready to host the new RES. Okay. Why that? Because you know that the transmission network was historically the part of the power system that connect the generation with the power system. Okay, so the big generators were already connected to the transmission network. That was designed to collect the energy that comes from the generators. Okay, so it seems that they are already ready to host more generation. But the problem is that connecting a large amount of RES on the high voltage networks, which are typically wind farms, has to be in any case properly managed. Okay, because you could end up in some technical and also regulatory issues. Okay. So here the idea is, okay, the transmission networks are in a good position to integrate RES, but be careful because there are some issues still. Okay. And one of the issues you can imagine is if I want to install most of the RES in the south and I have to bring this energy to the north of Italy, basically I would have technical issues because I don't have enough transportation capacity to bring this from the south to the north. Okay, and moreover, you have to be careful because the installation of DGs to the distribution networks can also affect the stability of the transmission system. Okay, so even if the transmission network is able to host RES, the RES that I'm installing on the distribution networks can affect also the transmission networks. Okay, so I would say the transmission networks are more ready than the distribution networks, but needs they need again some changes in the planning and operation. So basically, at the beginning, when the penetration of RES, especially wind farms, were lower, small compared to the total power production, we didn't have any problems. Nowadays, in recent years, since the production from wind farms has increased, may now have some problems also in the transmission network. Okay, and in this slide I try to make a scheme of all the problems that can arise in transmission networks. Okay, so the demand coverage, variability and predictability, control, management, stability, voltage regulation, etc. So in the next slides, I will try to show you in more details all these tasks, let's say, all these issues. Let's start from the demand coverage. Okay. So the first issue we have to face is the RES impact on the demand curve. Okay. So basically, if you consider to have RES and you consider the residual demand, okay, so the demand of the loads without considering the generation from RES, okay, it is interesting to see that basically the RES can impact the demand curve. Okay. For instance, during winter, no sun, the impact is negligible. Okay. I don't know if you remember the shape of the load. I show you last week. It was something like this. Okay, with the peak in the morning and the peak in the afternoon. Okay, P and T. This is for a day. Okay. So in winter time, where you do not have generation from PV, okay, you still have the two peaks, okay, one in the morning between 7 and 10, and one in the evening between 6 and 8. Okay. But vice versa, if you consider a summer day, look, due to the sun, to the radiation, the residual demand curve in the morning is flat. Okay. So basically, you have a complete different demand curve. Okay. Here I'm speaking about the residual demand curve. Okay. So the one without, for instance, PV production. Okay. And that's not that's not very good, okay, for the other generators. Okay, I would say the thermal one. Look, here the thermal has to do like this. Okay, like the production from thermal that has to follow the residual load as a peak in the morning, a peak in the afternoon. While here, look, the trend, it's more, let's say, stable. Okay, so the thermal power plants has basically to change completely their schedule day by day, months by months, seasons by season. Okay, So the first impact of the res is the impact of the residual on the residual demand curve, which is the curve that has to meet with the other power plants, traditional, hydro, etc. Okay. Here you have another interesting example, okay, that clarify for sure this point. So basically, you have in yellow the production from PV on the 9th of April 2012. Okay, so this is the classical bell curve of a PV. Okay, so the 4th and the 9th are Easter, which is a national feast here, Easter Day, one in 2010 and another one in 2012. Okay, so just 2 years between the two curves. Okay, what happens in 2010? Okay, so this is the load profile of one of the Italian region, in region Marche. Okay, in 2010, look, the demand of this region is always higher than 0. Okay, so this region receives power from other regions. Okay, and what happens? Basically, just after 2 years, in 2012, look, the load profile, the remaining load profile of Regione Marche is completely different, because the generation from PV cover almost all the load, and in some hours between 11 and 3, okay, so 11 a.m. and 3 p.m. There was also a reverse power flow. So here is negative. Negative means that in some hours, the power goes from Marche. The power goes from Marche to other regions. Okay. So in this area here, the power goes from Marche to other regions. Okay. So you can imagine that managing a transmission network that in 2 years, so just 2 years, move from the blue line to the red line is a mess. Okay. Because in 2 years, you don't have enough time to redesign, to rethink about the power system. And you have, but on the other hand, you completely have a change. You have a completely change in the residual load profile. Okay. So basically, the blue curve and the red curve is the power. Okay. So this is the power that my traditional power plants have to cover. So the one without the production from res, while this is the additional power that in 2010 the thermal power plants has to cover. Okay, look, they have to cover almost double than in 2010 rather than in 2012. That's not a very small difference. Okay, So what's the concept here? Okay, be careful because the RES are completely changing the load demand. Okay, so one of the impact is changing the load demand, so changing the schedule, the operation of the other power plants, the traditional power plants. The second issue is the variability and predictability. Okay. The renewable energy sources influence the operation and the dispatching, okay? Because they are variable and unpredictable. So especially wind and PV are very variable within, let's say, day, weeks, and seasons, and also unpredictable. As I told you already, the combination of the variability and the unpredictability of RES with the uncertainty of the demand, okay, because also the demand is a little bit variable and unpredictable, okay. I don't know if you remember one of the first slide I showed you. The TSO make a forecasting of tomorrow, and then there will be the real value of the load. And if you remember, there were two different curves which were very close but not so close. Okay, so that if you sum up this uncertainty with the uncertainty of RES, it's not very easy to balance load and generation. Okay, because one of the you could have one of the main problem is a lack of downward reserve. What does it mean, downwards? Downward is the reduction of generation. Reduction of the production from generators. Okay. So the fact of having a generation which in past years was programmable and nowadays is variable and unpredictable make the needed of having a high level of reserve. Okay, so what does it mean having a high level of reserve? It means that if I have to plan the production for tomorrow and I'm considering generation from wind and PV, I have to keep in mind that I need also some traditional power plants to be ready in entering in production, because if tomorrow the wind and PV will not the same as I forecasted today, I need other power plants to recover the lack of energy. Okay. So in that case, I need more reserve. So I need more power there waiting to be called. Okay. To be asked to enter in production, just to be sure that if my forecasting of wind and PV were not so satisfactory, I still need to supply the load, so I need other generators. Okay, and you can imagine that if I have to keep some generators warm, okay, I need to pay them, even if they will not produce. I have to pay them because they are ready for my call. Okay. So that's in a certain way increase the cost of dispatching. Okay. What about the variability? Look, here you have for each of the months and for each hour of a typical day, the mean capacity factor, okay? Look, let's consider August, and let's consider January, okay? So the August trend is over here, while the January trend is over here. So as I told you many times, the wind production is higher in it's higher in winter time and lower in summertime. Okay. Look, from August to January, we move from 0, let's say 20% of the capacity factor to 45% of the capacity factors. So I'm doubled, okay, the production. Okay, this is a thing that I have to keep in mind. Okay, the same P install gives me 20% of energy in summer and 45 in winter. Okay. And also, if I look to the trend during the daily hours, look, I basically have a difference, okay, between the trend, the summer trend, which is following basically the increasing and decreasing of the temperature, and the winter trend. Look, January is quite stable, while August has a ramp and the drops in daily hours. Okay. So if I have to plan to operate my power system, that's not very easy, okay? Because this is, if you make a parallel with a thermal power plant, here you have the availability of the fuel through the months and through the hour, okay? And you cannot change it, okay? The only thing you can do is to reduce the production, but basically this is the fuel you have available, basically, okay? This chart explains you very well, basically, the situation, okay? So let's consider to have this curve, which is the system demand, okay? And the light blue curve, which is the wind generation, okay? Here you have 1 day, okay? So this is day 1, and this is day 2, okay? What happens? It happens that in just 18 hours, so less than 1 day, there was a change of about 1.2 gigawatt of production from wind, okay? Look, here we're more or less 400, and here we, or maybe less, let's say. Here, okay, let's say 1,400, okay? And here 400, and here is 200, okay? So basically from here to here you have plus 1.2 gigawatt. So from here to here, which are more or less 18 hours, the wind penetration, so the percentage of load covered by wind, passes from 2% to 42%. Okay? So basically, there was a very strong increasing in the wind penetration. And as a consequence, the other generators, the traditional power plants, have to decrease their production to compensate the increasing, okay, from 2 to 42. So in this case, the RES increase, the other power plants has to decrease because the load is fixed, okay? So I have always to follow this curve here. If the penetration of wind increase, probably the other generators has to decrease in this way, okay? That's just an example, but the main thing is that this variation here happens in just 18 hours, okay? So the transmission network and the other generators has to be able to change their schedule very fast. What about the unpredictability? So the unpredictability refers to the fact that if I'm doing a prediction, a forecasting for the next hours, okay, especially for the wind, is not very easy, okay? Look, here I reported the mean absolute error in percentage of the production, okay? And look, from 2005 to 2009, we were able to reduce this percentage by from 35% to 15%, okay? So this is also due to the research from also from the academia, where many researchers started investigating how to improve the prediction of the wind production. Okay, so we are trying to reduce as much as possible the unpredictability of the wind, but still we are around 50%. Okay. And another thing is that the more is the time frame you want to predict, the higher is the error. Okay, so if you are at time 1 and you want to predict the production after 4 hours, you have 10% of the error. If you want to predict for 2 days later, the error increase to 15%. Okay, so it's easier, but that's quite clear, to predict something that will happen just few hours in front of you. Okay, so even here the TSOs that are running the power flow has always to wait the last hours before the dispatching to have a better prediction to set up the production from all the generators. Okay, so you have the load, you have the generators, you have to dispatch, so to select which is the power that each generator has to produce. The more you're getting closer to the time of delivering, real delivering, the more you have the knowledge of the production from REST, the better you can dispatch. But if you want to program the production of the next week today, it's not going to be very easy with the REST, okay? Because the variability and the unpredictability is very high. So that's the reason why nowadays the TSOs are pushing the regulatory authority to make to impose to the REST units to install a supervision and control instruction system, okay? So in this way, the TSO can communicate with REST, and in this way, the REST becomes something more, let's say, controllable and manageable, okay? It remains, again, the unpredictability and variability issues, but at least the TSOs are able to communicate with the REST power plants and to exchange some messages and to control the production. Okay? So one way of dealing with this issue is to make the system smarter and make communication between the TSOs and the power plants. Okay? So basically, the RES generation reduces the net demand, okay? So the power generation from the classic units, the conventional power, is replaced by RES injection, but the RES are unpredictable and they vary through the time. Those two charts here are just to let you know which is the increasing in the reserve requirements and decreasing in balancing cost, while there is an increasing in the wind penetration. Okay. So the more is the wind penetration, look, the more are the cost and for balancing and to keep the conventional power unit warm. Okay. So the two effects on having REST connected to the transmission network are an increasing in the reserve requirement and an increasing in the balancing cost. Okay. You have to imagine that all these balancing costs are then given to are then included in the energy bill that all the people are paying monthly. Okay. So the rest, if we are not able to manage them correctly, they can also increase the energy bill cost, which is not good for the people. Okay. So we have to find a trade-off. What happens in the situation of having a high available RES? Okay. So let's consider to have this load profile, the one in blue. Okay. And to have the production from RES has the green curve. Okay. What happens here? It happens that for some hours I have more production from RES than what is requiring from the load. Okay. So here you have the P from RES are higher than the P of the load. Okay. The only chance I have here to balance the production and the generation is to cut off the production from RES, or vice versa. Instead of cut off this, I can, maybe using a storage system or something, move this energy later on in order to reduce the energy from the classical units, which are normally producing CO2. Okay. So when the production from RES becomes higher in some period of the year to the load, I have two chances: or to cut off the production from RES, or to move this energy forward. And how to do that? Using storage systems, which could be electrochemical batteries or maybe hydropower plants, etc. Okay. Look, this part here, the black part, because someone could say, okay, I can reduce the energy from the conventional units. Okay, so I don't move energy here, but I just cut off this part of the energy from the conventional units, and I save the production from RES. But that's not feasible. Why it's not feasible? It's not feasible because this part, this black part here, is necessary, okay, necessary to guarantee, okay, to guarantee the security of the system, okay? So if I lose this part of production, the system will result in being unsafe, unreliable, okay? Because I need this power for the balancing, for the operational reserve, for the stability, voltage control, damping, etc. So this black part here is mandatory. So I cannot do what I've done here. So the only chance I have is to move this energy in another time, okay? Since we were speaking about stability, okay, one of the other issue which is related to the installation of RES is the inertia of the system. I don't know if you study the inertia, but basically the inertia can be defined as the resistance to change, okay? So the more a system has inertia, the more the system resists the changes imposed from loads and generators, okay? So you have to imagine that the inertia is provided by rotating synchronous machines that have EV rotors, okay? So basically, if you remember, a rotating synchronous machines has a static part, which is called stator, and a rotating part, which is called rotor. Basically, the inertia is given by the rotating part, so the rotor, which basically converts the kinetic energy of the rotating masses into electrical energy, okay? So you have to imagine to have something that is converting the rotating energy into electrical energy, okay? You probably know that if I'm so starting from a stable steady state, if the load increase, what happens to the frequency of the system? The frequency of the system decrease. Okay? Or, sorry, the generation decrease. On the other hand, if the load decrease or the generation increase, the frequency increase. Okay? So you have to imagine to have your rotor rotating, okay? And you connect the load. So the rotor is rotating at a certain speed, so at a certain frequency. If the load increase, it is something like you are trying to brake, okay, to make this rotor not working at the same speed, okay, but break it. So the frequency decrease. On the other hand, if the load decrease, it is something like you are opening a little bit the brake, so the generator start going at higher speed, so at higher frequency. Okay. Basically, and you know that, for instance, in Italy the frequency has to be stable around 50 hertz. In USA, for instance, is 60 hertz. Okay. Basically, if the frequency of the system goes away from 50, you can end up with a blackout. Okay. So the problem of having an unstable frequency is the problem of having blackouts, which is a disruptive thing in power systems. Okay. So the variation of frequency, just to go back to the end, the variation of frequency is proportional to the variation of power and also to the inertia. Okay. So if I have a variation of 2 megawatt, okay, and this affect the frequency with the variation of 0.01 hertz, for instance, and my inertia is 1 and my inertia is 2, okay. If my inertia decrease due to the installation of res, what happens? Let's say that it decreased by 1, so from 2 to 1, okay. Basically, with the same variation in power, I would have a bigger variation in frequency, which is not good for the system because it means that my system becomes more stable. Okay. So the fact of having a system with high inertia make the system more stable. Yeah, but what's the problem? The problem is summarized in this table here. If the generation of energy comes from hydropower plants or from combined cycle power plants or from thermoelectric generator, I have a certain value of inertia, 2, 5, 5, 10, 3, 8. But look here, the PV power plant, which are connected to the power system using some converters, has an inertia equal to 0. What does it mean? It means that if I rely in a power system with 100% of generation from PV, I will probably end up with an unstable power system. So with a power system that has a frequency that always goes up, down, so probably it will end up in a blackout. Okay. So the fact of having just PV power plants introduce some problems also in the system stability. It is not just a problem of covering the load, but also a problem in the system stability. Okay? So which are finally the challenges due to the fast growth and high penetration of RES? First of all, we need additional transmission line to transport wind power. In the case of Italy, from the south to the north. Then we need new operational rules to enhance system stability and system security. Okay. We probably need higher overhead lines transportation capacity when I have high wind. Okay. We need to have a real-time monitoring of the lines. We need to move from deterministic to probabilistic approach, because the generation from wind is probabilistic, is not deterministic. And basically, considering all these things, it has been done in Italy in the last year is to install some to install some energy storages in the south of Italy to be coupled with wind power plants. Okay. So basically, coming back to the first slides, it is true that the transmission networks are smarter, okay, are already a smart part of the power system, but again, the penetration of RES can affect mainly the stability of the transmission system. Okay, so one of the main issues is the stability. Okay. Okay, guys, I just suggest a 5 minutes break, okay, so that I can recover my voice. And after 5 minutes, I will show you, like in 50 or 20 minutes, the main impact of RES on distribution networks. Okay, but just give me 5 minutes to recover a little bit, and I will be back with the last slides of my presentation. Okay, so see you soon.
Yes, Professor.
Okay. Okay, so let's move quickly to the last part of my lecture. So now we will have a look to the impact of RES on the distribution networks. Okay. So different than the transmission network, the distribution networks basically have been developed, okay, with little or no generation installed. Okay. So basically they were designed just to host passive customers, not active customers. Okay. That's make a big difference with respect to the transmission networks. The DSOs, so the distribution system operators, design the distribution network using a fit and forget approach. What does it mean, this fit and forget approach? Basically, the DSOs oversized the distribution grid to avoid congestion during the lifetime of the power system. Okay. So it was not a very, let's say, smart way of designing the distribution network, but since in the past years, historically, we're just like a road and highway to bring power from the transmission network to the final users, they just oversizing the things and that's all. Okay. The distribution networks are operated, as I told you already, radially. So the energy flows from the primary substation to the lower voltage levels, and there is no voltage controls where the distributed generators are connected. Okay, so this architecture that was chosen when the DG was rare, nowadays with the increasing of DG can lead to several issues. Okay, so basically the distribution networks are in a bad position than the transmission system. Okay, this pipe chart here shows that at least in Italy, most of the DGs are connected to the medium voltage network. Okay, so are not connected to the low voltage network, are not connected to the high voltage network, but to the medium voltage network. Okay, almost 85%. So the most effective power part of the power system, part of the distribution network, is the medium voltage side. Okay, different than for the transmission network. Look, in distribution network, most of the power comes from PV. Okay, so most of the power comes from PV. And basically, look also this chart here. The power installed in the northwest, northeast, center, and south. Basically, the power from connected to the distribution networks is more spread, more equally spread through the entire territory. If you remember, the wind was more concentrated in the south. For PV, it is more concentrated in the center north of. So for the PV, especially for DGs connected to the distribution network, we have an equal spread in all the territory, okay? That's even this is one of the difference between this transmission and distribution. What happens in the last from 2009 to 2012? Look, of course, the number of distributed generators connected to the medium voltage increases, especially between 2010 and 2011, due to the incentives, okay? And the power, look, the power is the red arrow, the red trend. The power goes from more or less 1.5 megawatt to more or less 500 kilowatt. So basically, the number of DGs increased while the size of the DGs decreased. So we have much more the generators with lower powers, with lower power, okay? What about the low voltage network? For the low voltage network, again, we have an increasing in these years here, but more or less the power remain the same. So 10 kilowatt in 2009, and it goes to 15 kilowatt in 2012. Okay, so basically there was an increase of connection and a reduction on the average value of a single generator. So you have a more spread generation. Normally, to study the impact of RES on distribution network, we use the so-called nodal hosting capacity methodology. Okay? The output of the nodal hosting capacity is how much generators can be connected to a given network. Okay? So I have my distribution network, for instance, the one I showed you in the city of Milan. And I want to know how much power I can install before having some technical issues, okay? So basically, what's the idea? Let's consider to have 2 buses and 1 line in my power system. I take bus I, okay, and I consider to install here a generator, okay? Then I select my performance index, so the variable that I want to take into account. For instance, I could select the line thermal limit, okay? So maybe this line can carry 10 megawatt, which correspond to 100% of the line thermal limit, okay? What I'm doing is to increase the amount of generation. So I increase the power injected at bus I, and I check the power flowing on line IJ, okay? At the certain point, okay, the more I increase this power, So at a certain point, I can reach 100% of the line thermal limit. Okay, so I get this point here. Basically, this is the amount of generation I can host with refer to bus I. Okay, if I increase more the power, I will end up in an unacceptable deterioration, okay? Because maybe if I consider this power, basically here it will be 130% of the line thermal limit, so I can damage my line, okay? So this is more or less the approach that is following to study the nodal hosting capacity. And which are instead these performance indices? There are many, okay? I could consider the supply voltage variation, the rapid voltage changes, short circuit currents, unwanted line protection tripping, reverse power flow, possible line thermal limit. Okay, so when I'm studying the hosting capacity, I have to check if all or almost all these parameters are respected. Okay, so if I have a supply voltage variation which respects the standard, if the line thermal limits is respected, and so forth. Okay. Basically, if I'm studying the nodal hosting capacity, what it's good to take into account are three performance indexes. So the supply voltage variation, the rapid voltage changes, and the line thermal limit. When instead I'm considering the system hosting capacity, okay, so I'm moving from one node to the system. If you remember this scheme, this is called nodal hosting capacity because I'm studying each node separately to the others. The system hosting capacity consider a set of buses, okay, and not just one. So I consider a set of buses, which will be also the entire distribution network, and I check these performance indexes: short circuit, line protection tripping, reverse power flow, anti-landing, transmission network issues. Okay. So we just to give you shortly few results. We apply the nodal hosting capacity methodology on the Italian medium voltage system, which is composed at more than 60,000 buses, but we apply this only on 10% of the buses. And basically considering each bus a time, okay, so like 6,000 buses. For each of these buses, I install a generator of 10 kilowatt. I run a load flow. I check if my limits, if my performance index are met or not. If they are not met, I increase another 10 kilowatt. Okay. So again, I have my bus I connect a generator of 10 kilowatt. Okay. Run a power flow. I have some issues. No. Okay. I go to 10 kilowatt. Run a power flow. I have some issues. No. Goes to 30 kilowatt. I have some issue. Yes. My hosting capacity at bus I, so hosting capacity at bus I is 30 kilowatt. This is the results of one bus, and I do this for 6,000 buses. Okay, and I check the small voltage variation, rapid voltage changes, and line thermal limit. Okay. Before going to the results, just have a look to the definition of supply voltage variation. It is very easy. The standard says that the DSO has to guarantee that at each bus of the distribution network, we have a voltage level which is plus or minus 10% of the nominal voltage. Okay, so let's consider to have a bus, okay? So I'm considering low voltage network. So the nominal voltage in Italy is 230 volt. So each bus, this is a bus, has to have a voltage between 230 plus 10% and 230 minus 10%. Okay? So the DSO has to guarantee the voltage being in this range. That's mandatory. Okay? I will skip this because it's quite clear. One of the consequences of having DGs is that since you have an injection of power in a bus, you increase the voltage level in that bus. Okay, so let's consider to have in a passive network the orange line. Okay, so here you have the primary substation, and here you have the end of the feeder. Basically, if you install a DGs in bus 48, for instance, you increase the voltage of that bus, so the voltage of all the buses. Okay, so one of the impact of DGs is to increase the voltage level. Okay, and increasing the voltage level could bring some of the buses to overcome the nominal voltage plus 10%. Okay. So if I have much generation from DGs, I can have an over voltages. Okay. So the hosting capacity has to check if my supply voltage variation is okay or not. What about the results of the simulation? The results. So in this chart here, you have the maximum injection from DGs. Okay. And here you have the percentage of buses that overcome the performance index. So basically, what happens? It happens that, look, you have to reach 10 megawatt to have more or less half of the buses that violate the limit. Okay, so basically the distribution network seems to be quite stable in terms of supply voltage variation, because I have to reach very high value of generation from RES to have issues, technical issue in terms of supply voltage variation. Okay. What about the rapid voltage variation? So the rapid voltage variation are does not consider let's say the plus or minus 10%. Okay, so if the voltage remain here, I'm okay. But even if maybe the voltage remain in this range, plus or minus 10% of the nominal voltage, maybe I can have very rapid changes, no? So these rapid changes are not very nice for the power system, I would say. And they have to have a variation which is not too deep. Okay. So there is a standard, which is this one, that says that the variation of the voltage does not have to be too rapid. Okay, because that's create problems in the power system. Even here, this is the results of the simulation. So basically, even here, the system seems to be quite stable. Okay, so I have to reach very high value of power before having issues on the rapid voltage changes. Okay. The last parameter is the line thermal limit. Okay. So what happens? It happens that when I'm installing a generator in the distribution network, and this generator is producing more than what is consumed by the load, this power flow back to the primary substation. And if the power of the generator is quite high, I could end up in getting the line thermal limit of the cables or of the overlaid lines. Okay. So basically, having a high quantity of power could bring me to have to stress the cable or overlaid lines in the power system. Okay. For instance, here you have an example where if you install a generator in this bus here, 131, look, you have an overcurrent on this bus here, and also this and this. Okay, so you cannot install as much power you want, otherwise the cable are not able to take this power out. In this case, the number of buses affected starts with the power a little bit less than 10 megawatt. Okay. Already at 9, you have some issues related to line thermal limit. Okay. And also some issues are started at 7 megawatt. Why at 7 megawatt? Because it depends on the voltage level of the feeder, because you know that the power is proportional to V by E. So if you, with the same power, if you decrease the voltage, you increase the current. So basically, this feeder here are at 15 kV, this here are at 20 kV. So the lower is the voltage level, the lower is the power that you can inject in the power system, let's say. So to host distributed generators, is better to have higher voltage in distribution networks. Okay. So finally, just to summarize, this is more or less the results we got from simulation. So the supply voltage variation, I would say the plus or minus 10% of the nominal voltage, seems not to be an issue of installing RES in distribution networks. While the rapid voltage changes and the thermal limits are two issues to keep in mind. Okay. Basically, if I inject 10 megawatt in the current buses of distribution networks, almost all the buses, almost 100% of the buses have either a thermal limits issue or a rapid voltage changes issue. Okay, even if I install let's say 6 megawatt, I have a certain amount of buses that are not let's say don't like to have this RES installed. So basically, what are the outcomes of this simulation is that, please, if you want to install DGs, RES connected to distribution networks, you have to keep in mind that thermal limits could be a constraint, okay? And also derived voltage limits is a constraint to take into account. The supply voltage limits is not a big issue, okay? In any case, from the simulation, we got that 85% of the buses can host 3 megawatt of RES, which is not a short amount of power. So the distribution network are, as they are nowadays, able to host 3 megawatt of power. Let's consider that normally on a household, you install 3 kilowatt PV, okay? So basically, without any change in the power system distribution network, you can install already more or less 1,000 PV power plant, okay? So basically, the distribution networks are in a, in an average situation, that they are not very ready to host these DGs, but not even already in crisis, let's say. How to deal with SVV or RVC and LTL? So for the SVV, if we have a proper voltage regulation strategy, we can manage it. And for the line thermal limit, the only chance we have is to invest in new lines. Okay, so you have to put in place investments to increase the line thermal limit of the lines. What about the system hosting capacity? One of the main issues that we are facing, if we consider not just one bus, but the whole distribution network, is what is called reverse power flow. What does it mean, reverse power flow? So nowadays, or historically, the power goes from the, let's say, high voltage to the medium voltage side. But if you install generation, okay, on the medium voltage side, you will end up with the power flow that goes from the medium voltage to the high voltage, which introduce some problem in the network protection, automation techniques, etc. Okay, so it will be better if we want to help the current distribution network not to have reverse power flow. So to design the power produced from DGs not to be higher than the load. Okay, so the power from RES should be better to be lower than the power of load, so that the power still goes from high voltage to medium voltage. That can help the distribution networks. Here you have, for the case of Italy, the percentage of the time we have a reverse power flow in primary substation. Okay, so we have a power from medium voltage to high voltage. Look, for 1% of the time in July, 23% of the whole primary substation faced a reverse power flow for 1% of the time. So it's already a significant amount. If we consider instead 5% of the time, we have 15% of the primary substation that faced a reverse power flow. Okay, so one of the issue in terms of system hosting capacity of the renewable energy sources is the reverse power flow. So the flows goes from not from high to medium, but from medium to high. Okay, so I think it's time to be the lecture over. Maybe we are also a little bit late, and if you have question or answers, it will be my pleasure to answer you. I hope this lecture and the previous one were interesting. I try to condensate many things and information in just 2 lectures. Was not easy. I hope that you bring back home at least the general framework of the impact of RES on transmission and distribution, and I hope I did a good job with these lectures. Let's say I hope so, at least.
Yes, Professor. Thank you very much for today's lecture.
Thank you. And lastly, if I'm available, you can maybe add myself on LinkedIn or on the ResearchGate. I can also share my contacts here in the chat so that we can keep in contact. And in the future, if maybe you want to visit me in Italy for I don't know, an exchange program or for thesis or for PhD, just send me an email. I will be happy to host you here, let's say. I don't know if you want to switch on the camera just for a while so we can say bye-bye each other. I don't know if Professor Duong is still here or we can finish here. Okay, guys, so thank you again for being with me in these lectures, and hope to see you in the future, maybe. And have a nice Sunday from my side.
Yeah, thank you very much.
Thank you. Bye-bye.
Yes, bye-bye.
Bye-bye. Thank you. Thank you to all of you. Bye-bye.